Hi guys, so today we're going to talk about chemical bonding and the different ways in which molecules can interact. To do this, we're going to have to use our Lewis dot diagrams. And remember that Lewis dot diagrams are always going to use the valence electrons only. Okay, so for here our example is fluorine. If you look on the periodic table, fluorine is a halogen, and so it has 7 valence electrons. So we would represent that with 7 dots. All right, let's talk about what bonding is. Chemical bonding is the joining of atoms by strong attractive forces creating a new substance. You guys have already seen this in the lab. Ionic bonding is what we're going to talk about first. This is when we have 2 different charges. So it's when a positive is going to be attracted to the negative, or we call that oppositely charged ions. In this case, electrons are transferred. So one is going to steal electrons and one is going to give up electrons. This happens when an atom with low ionization energy and an atom with high ionization energy come in contact with each other. This is going to be between a metal and a non-metal. So if you remember, we said that the halogens often join with the alkali metals. So my example here is sodium, which is an alkali metal, and chlorine, which is a halogen. All right, so some things you need to know is that once you form an ionic compound, they are going to be neutral, and they're held together by electrostatic forces. And you can think about electrostatic forces being charges, so the positive and the negative, the forces between the positive and the negative charge. These, when they form together, are going to form what we call salts. Now, you're already familiar with sodium chloride being table salt, but actually anything that's ionically bonded in this way, we're going to call generically a salt. So these are all examples of other salts we can form. Characteristics are these are strong bonds, the strongest bonds, because one is having to give up electrons and one is taking those electrons. They are going to be held together very strongly through those electrostatic forces, the positive and the negative. They have high melting points, and they're going to be soluble in water. They also conduct electricity when melted or dissolved in water. So you can think of table salt, okay? So if we were to see if table salt conducts electricity, it would if it was in water. This is the same reason that you don't want to be out in water when in a pool or something during a storm, because it will conduct electricity. All right, so they involve 3 steps. I think we already know some of these. First, you have to lose an electron or more than 1 electron. Then the other one is going to have to gain electrons, okay? So here's our example of sodium and chlorine. Sodium has 1 valence electron. It's going to give it away because it wants to look like a noble gas. Chlorine has 7, and it also wants to look like a noble gas, so it's going to take that extra electron. Now when these are bonded together, it forms a very strong bond. Okay, and we call this a crystal lattice structure. So notice in this picture that it alternates between the positive and the negative ions. Okay, and they alternate in regular repeating patterns. That by definition is what crystal lattice is. You will need to know that for the benchmark. So look at these pictures and make a little print in your brain of them. All right, so some other examples, we could also form ionic bondings with things in the second column, so group number 2, with the group next to the halogens as well, so the oxygen column. These have, oxygen has 2 that it wants to gain, and magnesium has 2 it wants to give away. So these 2 are also going to be ionically bonded together. Remember that the positively charged ion is called the cation, and the negatively charged ion, in this case the oxygen, is the anion. Here's another one with lithium and chloride. If we're doing lithium and chloride, lithium has 2 electrons to give away, but chlorine only needs 1. So we would need 2 chloride ions to bond with that 1 lithium so that they both have happy noble gas configurations, or another way of saying that is happy full valence shells. Okay, they both look like a noble gas when they interact in this way. All right, so let's move to covalent bonding. Now I've talked a little bit about covalent bonding in general, and this is when the electrons are going to be shared. Okay, so nobody's going to have to give up electrons or take electrons. They're going to share electrons. These are going to be held together by the two nuclei, so that's the nucleus, those are the protons, being slightly attracted to the electrons. Some characteristics are we're not forming any ions, low melting points, so these are not as strong bonds as ionic bonding. They can also be brittle. They're also non-electrolyte or non-conductors. So when we think of covalent bonding, I always tell students to think covalent starts with C, and C is carbon. So covalent bonding is the bonding of carbon. And with carbon, we're going to bond carbon with all the things carbon likes to bond with, oxygen and hydrogen, nitrogen, all those molecules of life. Those are all covalently bonded together. So if the electrons, so say one has 3 electrons and one has 4, then it's not going to be so much of an ionic bond forming because neither one is going to want to give all of theirs away or take on that much, so they're going to share them between them. So here's some common examples that you should know. OH, we call this hydroxide. Oxygen has 2, and we can bond that with an oxygen there, or a hydrogen. If we have 2 hydrogen together, those also will form covalent bonding. Okay, so they're going to bond together there. Now, how can we tell how things are going to bond? Well, we have to look at the valence electrons. We have to see what we're bonding together and come up with which ones we think are going to be shared. We call these the lone pairs. So here are the steps for building more complex Lewis dot structure. For example, let's do ammonia, NH3. First, we have to decide on which one is going to be in the middle. We call that the central atom. The central atom is never going to be hydrogen. Why? Well, because it only has one space for bonding, it's going to attach itself to an end of something. So we're going to put ammonia in the middle, or sorry, nitrogen in the middle. Then we're going to add up the number of valence electrons that can be used. So here, hydrogen has 1 and nitrogen has 5. So that means we have 3 times 1 plus 5, which means we have 8 electrons or 4 pairs of electrons. Now all we have to do is make the pairs, because pairs of electrons are going to be the bonds, and we'll practice this in class as well. So the single bonds are going to be between the central atom and each surrounding atom. Each bond takes 2 electrons. Remember, they're sharing those 2 electrons. And then the remaining electrons you're just going to leave as dots, okay, on the end. We call these lone pairs, and a pair means 2. So we wouldn't say, if you look at that structure, that it has 2 pairs. No, we say it has 1 pair of electrons, which is 2 electrons that are lone. All right, and we're going to again practice some of this in class. Now we have to make sure that there are 8 electrons. So I'm going to count the nitrogen, and when you count a bond, you're going to count 2. And then check the electrons in your drawing to make sure that the numbers match up and that you didn't use too many. Here's another one. Let's do carbon dioxide. So we're going to put carbon in the middle and oxygen on the outside. So we have to add up. Carbon has 4 available bonding. Oxygen has 6 per each, so 12 total electrons, which means we need to account for 16 valence electrons total. There are too many electrons in our drawing, so if we draw it this way at the top, there's too many if you count them, including the shared pairs. So we have to move some of these into another bond. This is where double bonding and triple bonding can come into play. So we're going to move these lone electron pairs, and we're going to make them into bonds. And that way, we still can account for the electrons around our elements, but now we don't exceed the electrons that we came up with in our total, because you can't have electrons, extra electrons coming from nowhere. Okay, so that You always have to make sure that your electrons add up. Double and triple bonds are commonly observed, especially between these ones. So just maybe write these ones down. These are common ones. Anytime you see two lines, that is a double bond. Carbon likes to form double bonds between itself. It likes to form double bonds between it and hydrogen, or it and nitrogen, or sometimes triple bonds between nitrogen and oxygen. All of those are possible. All right, what else do you need to know about covalent bonding? Well, there are two types of covalent bonding. The first one is what we call nonpolar, and this means that the electrons are equally shared. The other one is polar. So polar is the opposite. It means there's a pole, or one of the pairs of electrons is pulling more than the other one. So it shares unequally. That means the electrons are going to be found closer to one of the other nuclei than the other. Why is this? Well, one atom has greater attraction to the electrons. And you don't have to really know anything about electron negativity, but this does increase the electron negativity. So, in fact, all bonds share equally or unequally. Okay? And here's just some examples. So these are real pictures, and you can see the pull of electrons, and that the electrons are not distributed evenly throughout the nucleus, but that the darker spots are found closer to one nuclei than the other. All right, and all of this we will cover later. But here we go. So here's our covalent nonpolar, that's hydrogen. So it's nonpolar, they look like they're sharing more equally. Polar covalent, so you can look over here, and the chlorine is definitely trying to hog those electrons a little more. And then you have ionic, where you don't have that weird area because they've transferred electrons. All right, the last type of bonding I want to talk about is metallic bonding. Now, transition elements, they're the transition metals, we said that they were a little strange, and the reason being that they share only the positive ions. Okay, so what happens, and this is what gives the metals their luster, okay, that shiny material, is the flow of electrons that flow from one element to another and back again over and over, kind of giving them that little sheen. Okay, and that is caused by the flow of electrons from the positive metal ions. Positively charged ions is another way to say that. So if you look at the picture at the bottom, this is a common picture that is used to demonstrate that this would be an example of a metallic bond. So anytime you see that it's the positive ions that are doing that's flowing, that's going to be an example of a metallic bond. All right, what else? This allows them to create heat and electricity. Electricity, by definition, is defined as the flow of electrons. They are shiny, again, because the electrons are attracting light. You'll learn that probably in college or physics. They are also malleable and ductile, meaning we can bend them and move them around. Okay, and this is, again, all because of the electrons. All right, so those are the three types of bonding that I want to talk with you today. So we talked about ionic bonding, we talked about covalent bonding, and the two types of covalent, which are nonpolar and polar, and then we talked about metallic bonding, the positive flow of electrons. All right, well, that's all we have for today, and we'll be doing more with this in class. Bye.